Oh, welcome back. This is the second in our series on integration. This one, integration by substitution. In calculus, as in almost anything at all, you can't have too many tools in your toolbox. This is another tool that you can use for calculus, integration in particular. And we're just going to go through this and use example after example, and you'll see how integration by substitution works. So here's our first example, and you can see that on the screen there. And we're going to integrate that. And first, to set up our substitution, we're going to set u equal to, x to the 8th plus 1. That's because this is a major component of this integrand. I'm not sure how to pronounce it. Now, while we've got this substitution started, we're going to also differentiate it because we're going to need that anyway. Because remember, we're going to look toward getting something like this. So we need this differentiated. So that'll give us 8x to the 7th, and we want du, so we're going to solve this for dx, and du equals 8 8x to the 7th dx, just multiply by dx. So the dx itself would be du over 8x to the 7th. Now what we can do is put that right in there. So what we've got is 8x to the 7th, and this is going to be u to the 5th. Check back here, there's u, it's taken to the 5th power, and instead of dx we're going to write its replacement, du over 8x to the 7th. See what's coming up? The 8x to the 7th cancels out. So what we've got now is u to the 5th du. Easy stuff, right? So what we get here, we don't need this anymore. We can take this directly. So be u to the 6th over 6 plus c. Remember, it's an indefinite integral, so we need that constant of integration. Now, once we've got this, we can put our u back in again. So our final answer would be u to the 6th, which is x to the 8th plus 1 to the 6th power over 6 plus c. And we've got our first one. There's our answer. Next one, we're going to find this indefinite integral, and I'm going to let the checking to you because that's good practice, because this is a good way to remember how to do the differentiation. So first, what are we going to set up? We're going to let u be this part down here, 5 minus 3x to the 5th. We need to differentiate that. and multiply by dx, so we'll have minus 15 x to the fourth dx. That's right here, isn't it? So I can rewrite this as du over u cubed. Or better yet, rewrite that as u to the negative 3 du. And we can use our integration power rule. What do we get? We get, remember, we're adding 1 to this exponent, so we'll have u to the negative 2, and we're going to have a negative 2 down here, negative 2, and remember, this is a 15x to the fourth. This is a minus 15x to the fourth. So what we'll need to do is put a minus out front, plus c. These minuses will cancel, and what we'll get is putting u back in from its original value. We'll have 1 over, because remember this is u to the negative 2, so in the denominator we'll have that 2, and we'll have 5 minus 3x to the fifth to the second power plus our constant of integration. Number 2 down. There's a cleaned up version of our answer. Next, we'll find the indefinite integral for this one. And to begin, what do you think u is going to represent? Well, if you guessed 3x squared minus 4, you'd be right. And you know you're going to differentiate, change this into a differential equation. So 6x dx. Now over here, we've got 30 times this. It would be nice if that were a 6, wouldn't it? Well, why not split this up? Make this 5 times 6x, 3x squared minus 4 to the fifth power dx. Now we've got the 6x dx, that's our du. So what we've got then is, if we put those two together, that's du. We've got u to the fifth power du, and the 5 out here. So, leaving that 5 outside, what do we have? U to the sixth over 6 plus c. So we've got 5 sixths. U to the sixth, we'll put the u back in, which is 3x squared minus 4. That's the 6th power plus our constant of integration. And we've got another one down. Next one. Let's move on to this indefinite integral. And you'll do the checking by differentiating. So how are we going to start? What do you think u is going to be? Well, if If you guessed 10x, you'd be correct. And if you guessed we were going to turn this into a differential equation, you'd be right. du equals 10 dx. Now, back over here, we've got 10e 10x dx. We'll change that to dx by itself, and e to 10x, or this will be e to the u du, and then we can take the integral of that. It'll be e to the u, that's pretty simple, plus c, and put the u back in. So what we've got is e to 10x plus c. There you go. Pretty simple. Love that e to the x function. At least I do. Nice and simple. Substitution makes it so easy. Next one. Hit pause, write down what you think u is. If you guessed 3x squared minus 6x, you'd be right. Turn that into a differential equation with 6x minus 6 dx. Notice you could write this also as 6. Oops. We need those 2's there, so why don't we do this? Make this 3 times 2x minus 2 dx. So what we can do over here is we need this 3, so we can use du. So since we need it to look like this, to put that 3 there and not change the value, that's our adjustment factor. So now I can write this as 1/3 e to the u, that's from this part over here, du. All of a sudden, it gets really easy. So it's 1/3 e to the u plus c. Put the u back in, 1/3 e to 3x squared minus 6x plus c. There you go. You catching on? There you go. And turn my page, turn your page. Next. Are you slipping ahead? I hope so. Let u equal the 3x cubed plus 5. Turning it into a differential equation. The u equals, and this will be 9 x squared dx. Notice over here we don't have a 9. So what we need is a 9 here. But to do that, we'll need to put a 1/9 in front, so we've got the same value. 9x squared, excuse me, over the 3x cubed plus 5 and dx. Here's our du right here. So we can write this 1/9 and this 1 over u, and these two together make up du, and that's easy to differentiate. 1/9 natural logarithm of, and don't forget the absolute value, because we don't know whether u is going to be positive or negative, plus c. Easy stuff. Then last thing we need to do is put u back in, the actual value of u, of 1/9, natural logarithm, put the u back in, 3x to the 5th plus, cubed plus 5, absolute value, plus c. Getting the hang of it? Not too bad, is it? Let's keep on going, because I know you're enjoying this. There's a nice cleaned up look for our answer. Let's move on to the next one. In fact, maybe you want to hit pause. See if you can do it by yourself. Okay, you're back. Well, let's get this rolling here. Let u be the 3t plus 4. That's the inside function. That should sound familiar. So du would be 3 dx. Now, that's dt. Did you catch that? Good. Now we have dt over here, but we don't have the 3, so we can get the du in here. So I need a 3 up here. That means I'll have to put 1/3 out here to keep the same value. So the 3 and this dt over here. And on the bottom, we've got 3t plus 4 squared. We can rewrite this again as 1/3 3 dt, leave this out here, and the 3t plus 4 minus 2, because we can use the general power rule. So we'll have 1/3. This is just u to the negative 2 du. Just use the power rule. U, add 1 to this, that becomes a negative 1. Also put the negative 1 on the bottom, and plus c. So where does that take us? We've got a negative 1/3, because we've got the 1/3 and we've got the negative 1, and that's u to the negative 1, which means we'll have a u down there, plus c, and then we'll reestablish the u in its original version. So we'll get minus 1 over 3 times 3t plus 4 plus c. And there you go. We just got through one more. Well, let's keep moving. There's our nice clean answer. Next one. Take a look at this one. This one's a little bit trickier. So, we're going to let u be x plus 1. Differentiating, we'll get the differential equation 1 dx, or just dx. Then we're going to have this looking like this. So now here's the sort of weird one right here. We've got x. What's x equal to? X is equal to u minus 1. So this is an unusual one. This x is u minus 1. Going back to our substitution. The second part would be the square root of u. And since du and dx are the same, there's our integral. Now, remember this is u to the 1/2 power. So we can rewrite this integral. We're going to multiply this u to the 1/2 power times the u minus 1, which will give us u to the 3/2 minus u to the 1/2 du. Now remember, we can split this up just as we did with differentiation. So we can make this the integral of u to 3/2 minus the integral of u to the 1/2. And we've got du's with both of those. Now we can just use the power rule. So we'll have u, we'll add 1 to the 3/2. That gives us 5/2. It'll be divided by 5 over 2 plus the first constant minus, and we'll take this, we'll add 1 to that, we'll get u to the 3/2 over 3/2 plus another constant. Of course, we're not going to leave it like that. We're going to keep the u's for just one more step. So divided by 5/2 means multiply by 2/5. So this will be 2/5 u to the 5 over 2. Now we're going to combine those two constants, so hold off there a moment. Minus 2/3 u to the 3/2 plus, and combining those constants, we'll just call it one big constant of integration. Now it's time to put everything back together from our expression over here. We'll have 2/5. The u is x plus 1. 5 halves minus 2 thirds, x plus 1 to the 3 halves plus our overall constant of integration. And there you go. Now, to be honest, when I first tried this, I went off in a couple of different directions, and some of those didn't work. I guess the moral of the story is, if what you're trying doesn't work, try some other things. Find one that works, hopefully. Okay, there's our cleaned up look. And we'll move on to our next one. Alright, you want to make a guess on this one? Okay, we're going to let u equal to x minus 7. This one isn't quite as unusual as the last one, fortunately. Now, with that said, what we've got here is the integral of u plus 7 will be an arrangement sort of like we did before in the last one. And on the bottom, we'll have u to the 1/2. And forgot there, du equals dx, so dx can be written as du. So what do we get? We have u plus 7 over square root of u. So we've got, we're going to split this up. We're going to divide both of these by u to the 1/2 power. So u to the 1/2 into u gives us u to the 1/2. It's 1 minus 1/2 is 1/2. Plus, we're going to go ahead and split these. We'll have 7 over u to the 1/2. And of course, both of those have du after them. Next, this will give us the integral of u to the 1/2 du, plus, we want to set this up so it's easy to work, the integral of 7 u to the negative 1/2 du. Now, time to integrate. Add 1 to this, and we'll get u to the 3 halves. That'll be over 3 halves, or times 2 thirds. Remember, if you're dividing by a fraction, invert and multiply. Plus, now we're going to combine those two constants of integration, so hold off on that. Over here, we've got 7, and this will be u. Let's see, this was u to the negative 1/2 there. Clear that up a little bit. So add 1 to that, and we've got u to the 1/2 divided by 1/2, which means we multiply by 2. And there's our combined constant of integration. So what do we get? We've got 2 thirds, and put the u back in. U is x minus 7. That's the 3 halves power, plus 14. And we've got u, which is x minus 7. And that's to the 1/2 power, or square root. And those are combined constant of integration. And there we go. Not too bad, is it? Okay, there's the cleaned up version. And this wouldn't be complete without an example that touches on real life a little bit, right? So here's an application. And unfortunately, I put the answer in here. So here we go. So we've got the weekly marginal revenue. So this is the differentiated version. So we want the actual revenue function itself. So we're going to take the integral of the marginal revenue dx. So what do we have? Well, the marginal revenue is 30 minus 0.001x plus 300 over x dx. Make both those brackets. Now we've got some other information for one, let's see, what is it? 1 week. Our marginal revenue is $50. In other words, one more belt, $50 more. We want to find the revenue function. If you look back here on some of these other ones, we always had that constant of integration, and we didn't know what it was. But with this information right here, we're going to actually be able to find out what the revenue function is, and not just some function plus c. So, what's our integral look like? Well, first of all, we can split this up. 30 dx minus, and we can bring this 1,000th out front. That'll make this a lot easier, right? Plus, I'm going to bring this one 300 out front too. 300 integral of 1 over x dx. That should look pretty nice. So, bring this 30 out front or not. If you remember one of your properties, oops, excuse me, this should just be 30x. Here we'll have minus 0.001, and this will give us x, not to the 1, but x to 2 over 2, plus 300, and this will give us the natural logarithm of the absolute value of x, plus c. Let's clean up a little bit more. So this gives us 30x minus, and we've got division by 2, so we've got 0.0005 x squared plus 300 natural logarithm of the absolute value of x plus c. Now this is where knowing the revenue for one item comes in. Put the 1 in for the x's, and you should end up with a 50. So here we go. 30 times 1 minus 0.0005. Fortunately, this 1 squared is still 1. And you've got 300 times the natural logarithm of 1 plus c. We're going to find out what that c is. And this, from this information up here, it should be a 50. So what do we get? Let's see, we've got 30 minus 0.0005 plus this part right here is 0 because the natural logarithm of 1 is 0. So that's gone. We don't need it. And that's equal to 50. And the C goes in there, sorry. Almost lost it. We were looking for that. This tells us C is very close to 20. As a matter of fact, we're talking about dollars and cents, so when you take 50, subtract 30, and add 0.0005, it's $20. And we've got our revenue function. What's our revenue function? Well, we had our revenue function pretty much right here. All we need to do is fill in the C. And our revenue function, 30x minus 0.0005x squared plus 300 natural logarithm of x plus, and we did find c down here, plus 20. Now the word two questions said find the revenue function, but also find the revenue from the sale of 500 leather belts. Easy. Don't get lost. All we need to do is put the 500 in for how many belts. Put that in for all the x's, and the revenue from 500 belts would be $2,692.35. Actually, well, 36, sorry, 36. There you go. And that's it. In case you had wanted to look at all the answers at one time, maybe work those out separately, there's a list of all the answers in one place. So if you want a copy of this slideshow, just let me know. I can send you a copy. You can work through those, and as you run into a problem, you can look at this answer sheet, see if you got it right. If you have problems, just let me know and we'll get you straight. Remember, send a picture of the actual problem, show what you did, and I'll get you back on track. Until next time, we've got one more lesson of integration. We're getting close to the end. Until next time, keep smiling and take care. Bye-bye.